So now that we have basically figured out exactly how to write an equilibrium constant and how to manipulate them, or how to add up different versions of Kc, now we should probably have a look at exactly what they do and what they mean to us. So this reaction you'll see quite a bit in the next few weeks, but it is acetic acid dissociating. So we have 7 strong acids that we've learned earlier in the course, and basically pretty much everything else is a very weak acid. And our next unit will deal specifically with acids and bases, but here we're actually going to look at what a weak acid is. So this is an organic acid. It has this the C double bond O's and the COH on it. So we call these carboxylic acids. And they behave in a manner that we consider to be a weak electrolyte, or in other words, a weak acid. And all that means is that when you put a concentration of acetic acid into solution, it doesn't all produce H plus, which is the acidic proton. Now, ignoring all of the acid and base theory, we basically just treat it as a two-way reaction. We'll have acetic acid breaking up, forming 2 ions, and then it'll recombine and go back to the reactant side. So we have 2 reactions, and they form an equilibrium where forward and reverse reactions are equal. So we have the question here says an aqueous solution of acetic acid is found to have the following equilibrium concentrations at 25 degrees Celsius. So equilibrium constants are temperature dependent. So the equilibrium concentration, if we do it in the lab at 22 degrees Celsius, and then we do it later in June at 31 degrees Celsius, we'll get different answers. It might not be drastic, but they will of course change. So the first thing we're always going to do is we're going to write the equilibrium expression. So I'm just going to write Kc here because we're going to deal with concentrations. Technically, we're going to learn that this is actually, because it's an acid, it'll be called Ka for the equilibrium constant of a weak acid, but we're going to use Kc for right now. Concentration of your product over your concentration of your reactant. So there's our equilibrium expression. Now, the key to this particular problem is you have to see the word equilibrium concentration. So it says the following equilibrium concentrations, which means that we are just going to take the concentrations as they are listed and put them into the equilibrium expression that we learned to write in the last lesson. So the concentration of H plus is 5.44 times 10 to the negative 4. The concentration of the acetate ion is the same. We probably could have just written a squared here, but parentheses. The square parentheses are reserved for when you're talking about a concentration of, so you try and stick with using the rounded parentheses, but it's not a huge deal. And one. So we solve 5.44 and we have Kc is equal to 1.79 times 10 to the negative 5. And that is the equilibrium constant. So at 25 degrees Celsius, no matter what we do, with regards to however we prepare it, if it is at 25 degrees Celsius, the ratio of the products to the reactants will equal that number. And that is the point of doing this, is that we know what the ratio of products to reactants has to be, because we know where the equilibrium is. And that's kind of a big idea. When we look at particular reactions, we know that if KEQ is equal to 1, then products in reactants are equally favored. If KEQ is less than 1, is less than 1, then we know that it is the denominator is going to be much bigger than the numerator, which is exactly what we see here. So we know that equilibrium lies with the reactants. And then if KEQ is greater than 1 or a lot greater than 1, then we know what lies with the products. And that just, when we use that type of language, when we say that equilibrium lies with the reactants or lies with the products, what we're talking about is, yes, there's a forward and reverse reaction going on, but it is possible that there is more product um, than reactant. It doesn't have to be equal concentrations. All we're saying is that when the thing is at equilibrium, or the chemical equation is at equilibrium, that the rate of the forward and reverse are equal. We're not saying that the amounts are. So question 2 sort of takes us into the next big idea, and that is the use of what we call the icebox. So it's very unlikely that we're going to be measuring in exactly equilibrium quantities of a chemical species. So for example, if I put in zero point 0.5 atmospheres of SO3, and let's assume that there is some SO2 and oxygen present, it's very unlikely that that is the right amount to satisfy the equilibrium constant. In other words, it's very unlikely that it's going to be perfectly balanced. If you were to take, a regular scale and put random weights on both sides, it's very unlikely that the scale is going to be perfectly balanced. It's possible, but it's very unlikely. So that's the whole idea here. So first we're going to introduce to you the Icebox. And the Icebox just is an acronym, and it means initial change in equilibrium. So initial change in equilibrium, or Icebox. And it's basically just a way for us to do a little bit of bookkeeping. So I've written the reaction on the top. And sometimes people like to put like a double line in between reactants and products. So we're just going to use this to actually organize our data. So first of all, it says initially. So there's a keyword, some keywords here. So you see initially, and then it says at equilibrium. So we're going to that tells us where we're going to put the information. So it's initially. So that means we're going to put it in the I line. The vessel is charged with 0.5 atmospheres. So 0.500 atmospheres. And again, the temperature is given because this is temperature dependent. I don't actually need it at all for my equation, but it is kind of important that we do know what that is. But so on the first line of that question, it doesn't tell me that I have any of this. So I'm going to assume that they're zero values. It says at equilibrium, the SO3 partial pressure, so that's the reactant, is 0.200, and we'll figure out significant figures later. And that's what the question has given us. Now, we're going to try and fill in the change lines using a little bit of stoichiometry. So, first of all, I have 2 moles of SO3 going to 2 moles of SO2 and 1 mole of oxygen. So it's 2 to 2 to 1 ratio. Now, if we start with 0.5 and we end with 0.2, that means that the change is going to have to be negative, because we're losing it, 0.3. Now, because the 2 moles of SO3 is consumed to produce 2 moles of SO2, then these values are going to be the same because they both have a 2. But on the product side, we're going to have a plus. Now, the ratio of SO2 to oxygen is 2 to 1. So for every 2 moles of this that I produce, I'm going to actually only get half that much of oxygen. No matter what you do with an icebox, you always add the I and the C line. So 0.5 plus negative 0.3 gives me 0.2. So 0.3 and 0.150. So this goes into your Kp expression. Just the equilibrium line can go into a Kp expression. So we first of all, we'll write it out. Kp is equal to the partial pressure of the products so we write out our expression just like we did in our last lesson. Now we're just going to put in our values from our equilibrium line or our E line. So the partial pressure of SO2 and oxygen, 150, 0.300, 0.200. And you got to remember that you do have to square them. It's a very common mistake that's made. So we have zero point 0.3 squared times 0.15. So the numerator is 0.135. Be 0.0. So 0.0, 0.0, and this equals 0.338. And that would be equal to the value of Kp. So basically, at all situations, the ratio of the products to the reactants has to equal that number. So if I were to now that I know that number, if I were to change this number to 0.7 or 1 atmosphere, I can figure out how much product will be produced because I know the ratio of reactants to products has to be equal to that number. And yes, we do have to take into consideration the squares, which is the one reason that this does get a little bit more complicated. So now that we can do simple calculations using an icebox and determining what Kc is, we're going to look at something called the reaction quotient, symbolized by a capital letter Q. So, like I said, is we only can put equilibrium values, the E line, into equilibrium expressions. It is foreseeable that we are in a situation where we do not know if we are at equilibrium. So, in this particular problem that we're going to get, we're going to be given the Kc for the reaction at 50.5. We're also going to be given information with regards to how many moles are present at a particular time. And the key to this situation is that we do not know that if it's at equilibrium. That's what we're going to try and determine. We want to know if the reaction is at equilibrium. So the reaction quotient is written exactly like the equilibrium expression. There is literally no difference. The only thing that is different, and mathematically it's the same, the only thing that's different is that we use Q when we are trying to determine if the reaction is at equilibrium. In other words, are the forward and reverse reaction rates the same? So when we do that, we have to use the variable Q. So when we get to the scenario where we can solve for Q, we know that when Q is equal to KEQ, then the reaction is at equilibrium. That means Q and KEQ are the same, so you've entered equilibrium values. When Q is less than KEQ, the equilibrium constant, that means the reaction is moving forward. If Q is greater than equilibrium constant, that means the reaction is moving backwards. It's trying to get back to that point, which it's trying to rebalance itself. Because remember, no matter what happens, the ratio of products to reactants raised to their coefficients has to be equal to KEQ. So let's have a look at exactly what we see here in number 3. It says we have the equilibrium constant as 50.5. Predict from which direction the reaction will proceed to reach equilibrium at 448 degrees Celsius if we start with these number of moles. So the first thing we do is we write the equilibrium expression and it's given us Kc, so we have to use concentrations. And just like I have said, the expression for Q is exactly the same. It's just what we're calling it. So we're going to solve for Q. Q is equal to the concentration of HI. But before we start throwing numbers in, we have to understand that it is asking for moles per liter. And it's giving us moles and it's telling us it's in a 2-liter flask. So all of these numbers have to be divided by 2 to put them in as concentrations because we need to report it in moles per liter. So instead of writing in 0.02, I'm going to write in 0. 0.001 squared. And instead of writing in 0.001, I'll write 0.005. Just like that. Q is then equal to 1.33 when you do that calculation. So since Q is less than 50.5, the value that we were given, the reaction is moving forward. In other words, towards products. And that's how we use Q. We can use Q at any time, whether if we need to know if we are at equilibrium or if we're moving towards equilibrium. So the final big piece of equilibrium calculations is when you have an equilibrium constant and you're being asked to determine what the equilibrium values will be. So once again, we're going to use the Icebox, and we're going to deal with the same equation that we had before. So the equilibrium expression from above is just been rewritten. And we're going to do exactly what we had done in the past, is we're just going to fill in the information that we do have. First of all, we have 1 mole, so we have to make sure that we turn that to concentration. But luckily, it's a 1 liter flask, so we're going to have it in moles per liter without changing the numbers. So 1 mole of H2 and 2 moles of I2 are filled. We have heard nothing about the amount of product. So we have 2 reactants being put into a flask. We have no product to start with. Obviously, those reactants are going to combine and form some product. And the amount of that product is controlled by that 50.5, or the equilibrium constant. So we don't really know what's going to happen yet. So we're going to have some unknowns. We know that the ratio of hydrogen to iodine is 1 to 1. So we know that we're going to lose some amount of that. So minus x, because we don't know what it is. It's going to have to produce Hi, but so we're going to have a plus. We're going to produce some unknown amount. But because the coefficient is 2 to 1, we're going to write plus 2x. So that's really the only place, other than the exponents, where you're going to take into account the stoichiometric ratio. Then, as always, you add up the lines. And I'm going to lose a little precision here just to make my life a little bit easier. So we have our equilibrium line, which now has variables in it, or an x. So basically, just like we did before, is we're going to plug those in. So we have 50.5 is equal to concentration of Hi, so 2x squared over concentration of hydrogen So we now have a polynomial where we're going to be producing a quadratic equation out of this. So first things first is we're just going to go 50.5 times 1 minus x. 2x squared is equal to 4x squared. And then we just basically start creating our expression. So we expand our terms. Making sure we do have the right signs in here. Make sure you have your minus in. And then we multiply everything by 50.5. I have 4x on this side, so I'm going to bring it over. So now I have an equilibrium expression that's been resolved into a quadratic, and it's in the proper form to use the quadratic equation. So we can go ahead and put this into the quadratic equation if we'd like, um, but most times it's a lot easier just to solve it. So when you solve the quadratic equation for the two roots, you will get two roots, both real and both positive. You're going to have 0.935, and your second root will be 2.32, I think. So you have two roots, they're both positive. If you had one that was negative, you'd be done right away because you can't have a negative x. So then you look at the two roots and then you go back up to your equilibrium line and you say, okay, which one makes sense? And you cannot use the 2.32 because 1 minus 2.32 will give you a negative concentration. And a negative concentration doesn't make any sense. So your value of x has now been solved. You know what it is. It's 0.935. And you're just going to sub it in wherever you see x. So the concentration of H2 is equal to 1 minus x, which is equal to 1 minus 0.935, which is equal to 0.065. And that is in moles per liter. The concentration of I2 is equal to 1.065, just one more mole. And the concentration of HI, you're not going to double it. And I see people do a lot of things where they end up trying to take that 2 into account in a weird way. Basically, you're just going to multiply 9. You'll have 2x, and you'll basically just multiply it by 2. And that's where you've already taken it into account by when you created your quadratic, so there's no need to try and do something fancy. So you have your three variables here. You have concentration of HI is there, concentration of I2, and you've solved the question. And that's basically how you do it.